In this presentation, we will consider conditions of normality for sampling distributions of both sample proportions and sample means. We begin with a brief review of some concepts related to normality of one-sample proportions. Recall that categorical or qualitative data is behind what we have been looking at in chapters 5 and 6 when studying inferential statistics techniques for one-sample proportions. An example of such a case would be, we wonder what percentage of U.S. voters voted for candidate X in the last presidential election. In gathering data, we would only have two responses, yes or no. And then from those responses, we would calculate the proportion of yes answers. To apply the inferential techniques that we've learned and thereby attempt to answer the question on the previous slide, we need to know that our sampling distribution of sample proportions for a fixed sample size is approximately normal. Then we can use the central limit theorem to target the population proportion and establish a formula for the standard error. So the question naturally arises, what conditions need to be met to use the central limit theorem? We saw in chapters 5 and 6 that the conditions that needed to be met were independence and the success-failure condition. When going through inferential statistics techniques, that is, confidence intervals and a hypothesis test for proportions, which we looked at in chapters 5 and 6, we saw the logic of the success-failure condition, making sure that we take a large enough sample so that the number of successes and failures is greater than or equal to 10 will lead to an approximately normal distribution of sample proportions. The only wrinkle that arose was that we did not know the population proportion. So to get around that issue, we used our sample proportion as an estimate for the population proportion when checking the success-failure condition and to calculate the standard error. Now that we've done a brief review of some of the considerations we looked at in talking about one proportion inferential statistics techniques, let's turn our attention to what we are going to start looking at in Chapter 7, which is one sample means. We know that numerical or quantitative data is behind what we're going to look at in Chapter 7 when studying inferential statistics techniques for means. Here's an example. We wonder, what's the average height in inches of all SRJC students? In gathering data, note that there's a range of possible numerical responses we could obtain. It's not going to be a matter of just looking at two possible responses as we saw when working with proportions. So from the numerical responses we could gather in this case, we would calculate the average height in inches. So as was the case when we worked with proportions, to apply the inferential techniques we've learned in chapters 5 and 6 and thereby attempt to answer the question on the previous slide, we need to know that our sampling distribution of sample means for a fixed sample size is approximately normal. Then we can use the central limit theorem to target the population mean and establish a formula for the standard error. However, unlike with categorical variable data, numerical variable data for a population will already have some sort of distribution associated with it. In most cases, that distribution will be approximately normal. So, how does that alter the conditions we need to check to ensure approximate normality of the sampling distribution of sample means, and thereby be able to apply the results of the central limit theorem? Well, we still have two conditions that we need to check for, independence and normality. Now, since independence is met by taking a simple random sample from the population, just like it was when we were considering one sample proportion problems, we're going to go ahead and focus on the normality of the sampling distribution of sample means condition. So focusing on the normality condition for one sample means inferential statistics, our text provides two rules of thumb for checking the normality of the sampling distribution of sample means condition. The first is that if the sample size is less than 30 and there are no clear outliers in the data, then we typically assume the data come from a normal population distribution to satisfy the condition. What about if n is greater than or equal to 30? Well, if that's the case, and there are no particularly extreme outliers, then we typically assume the sampling distribution of sample means is nearly normal, even if the underlying population distribution is not. So to explore the two rules of thumb for normality that I just discussed on the previous slide, we're going to go back to the Art of Stats website. So I'm at the Art of Stats website, and we're looking at some real population data. The variable for this horizontal axis is the amount of college debt. We see that the distribution, the shape, is approximately normal. And let's say I go ahead and take 10,000 samples of size 8 from this population. So I'm going to go ahead and take 10,000 random samples of size 8. And what I want you to look at is the bottom distribution that is shown for the sample mean X bar. Notice that the sampling distribution of sample means is approximately normal, very close to normal. And again, this is a small sample size, size 8. In fact, if I lower the sample size a little bit more, we see that the distribution of the sampling distribution of sample means still stays approximately normal, a little bit of a jag at the top. But if we increase the sample size, we see that the sampling distribution of sample means becomes very highly normal. In fact, as I get close to this value of 30, we see that it just gets more and more normal as I increase the sample size. So what this portion of the demonstration shows is that if our original population distribution for a variable is approximately normal, then no matter how small or how large the sample size is, we can be pretty well assured that the sampling distribution of sample means will be approximately normal in that case. Now let's change our population distribution so that it is bimodal. And again, I'm going to lower the sample size to, let's lower it down to 8. And let's see what happens when I draw 10,000 samples of size 8 from this new population distribution, which is bimodal. Well, in this particular case, we can see that the distribution is kind of sort of normal with maybe a little bit of, on the top here, it looks like it's a little bit flat, let's call it. Let me lower the sample size a little bit more to 6, and now we can start to see that it is definitely somewhat bimodal for the sampling distribution of sample means in this case. So small sample sizes being drawn from a bimodal population distribution do not result in a sampling distribution of sample means that is approximately normal. So let's increase the sample size and watch what happens to the sampling distribution of sample means as I do so. So I'm going to increase it to 22. There it's starting to look a little bit more like a normal distribution, but there's still a couple of peaks at the top that show the bimodal nature of the population distribution. So let's go up to 30. And once I reach 30, now we can see that the flattening at the top is starting to disappear. There's a clear peak that's in the middle, centered at the population mean mu. And if I increase that even more so, we see that the sampling distribution of sample means is clearly becoming more of a normal distribution. So that helps us to see why this cutoff value of 30 is so important in our normality condition check for sample means inferential statistics. All right, so for our last example of population distributions and the results that we see in the sampling distribution of sample means, I'm going to change this to a skewed distribution, extremely right skewed distribution for the population distribution. So again, let's take 10,000 samples. I have a sample size of size 5 for all of the samples I'm drawing. And notice what happens here. The sampling distribution of sample means is definitely right skewed also. It's definitely not normal. So if I go ahead now and increase the sample size, I'm going to bump it up to 22. Now we start to see it's becoming more strongly a normal distribution. And again, as we get closer to that magic value of 30, at 30 we can definitely see that the sampling distribution of sample means is approaching a normal distribution shape. So again, this helps us to see that when we have a population distribution that is not a normal distribution to begin with, that value of 30 is a critical cutoff value for ensuring that the sampling distribution of sample means is approximately normal. One last thing I want you to see is that this sample that I've drawn here looks like there's a value on the far right, this last sample of size 30. Looks like that could be an outlier. Let's see if that's true. We've got a mean of about 8.79. Going up 3 standard deviations would be adding approximately 21 or 22 to that. And we see that that value is starting to get to be somewhat of an outlier there. Could potentially be a clear outlier in that case. Let's draw a couple of samples of size 1 to see if we can have a case where there is an outlier. There we go. Here's a case where we have a sample mean of 13. And if I go up 3 standard deviations above that, that would be 33. Above that, that would be 46. This particular value, which is far beyond that, 33 plus 13 is 46. This is way above that. That's more than 3 standard deviations above the mean. And so that helps us to see why we have to be careful when we are looking at population distributions that are not normal, and we have a sample that may have some clear outliers, why we have to be careful about the sample size that we are taking when we do our checks for normality. From the Art of Stats website, we now clearly see the logic of the rules of thumb for checking the normality condition. However, for being able to use the central limit theorem, there is still one remaining wrinkle. We don't know the population standard deviation. So we use our sample standard deviation as an estimate for the population standard deviation to calculate the standard error. And we also use what is known as the t-distribution rather than the z, or normal distribution, to model the sampling distribution of sample means. And that concludes this presentation.